All right, hi guys, welcome to Science Week 27. Hope you're all ready with a piece of paper and a pencil, and let's get started. So, very first, if you guys would write down two things that you remember from last week's lesson, whatever those two things are, write them down. And while you're thinking of that, it's been so fun to be able to get your pictures of your work, and sometimes I get your little faces in there too. I love it. So thanks for sending them. Keep them coming. I love it. They're the best. And your guys' thermoses were so super creative. I'm still getting some pictures in. Someone used toilet paper. It was toilet paper in between like tinfoil. It was super cool. I can't remember who it was. But anyway, they used toilet paper inside their tinfoil, and they made like a cup out of their tinfoil. So super creative, super smart. I'm loving these. It's keeping you guys busy and active on experimenting for science. So keep them coming, keep it going. All right, hopefully everyone has two things from last week. We're gonna move on today. So today we are going to be discussing weather and climate, and what is the difference between weather and climate? I want you to think of that while we watch this video. I'm gonna go ahead and get my screen ready. Computer sound on. Share. Here we go. It's this video. So be thinking of what is the difference between climate and weather. Maybe full screen here. Come on, technology, work for me today. Oh dear. Okay. Yes. Here we go. Maybe.
Have you ever wondered what climate was like on Earth hundreds or thousands of years ago? This is the same question that scientists are asking. So one way that they can look into the past is by studying ice cores from glaciers to get an idea of what the climate was like so many years ago.
What's the difference between weather and climate?
Weather is basically the hour-by-hour, day-to-day changes that we see. You go on TV and you watch the weatherman to see what it's going to be like in a few hours, maybe even towards the end of the week. Climate is basically the overall average of what happens in an area on a scale of years or decades or centuries.
I see. So, weather looks at one day, while climate looks at the average of many days. Now, this average tells us what it's normally like in a certain place. Let's take a look at Forks. No, not that kind of Forks. Forks, Washington. From 2003 to 2009, it rained an average of 117 inches a year. Now this tells us that it's normally rainy in Forks, Washington. Now let's compare this to Las Vegas, Nevada, where the average annual precipitation is only 4.13 inches. We can see that the climate in Forks is wet and the climate in Las Vegas is dry. Now that we understand how to determine climate, how do we find out what the climate was like on Earth hundreds or thousands of years ago? This is where glaciers come in. What is a glacier?
A glacier is basically snow that has accumulated over many, many years. It will drop down and it will stay there without melting, and it will just continue to snow year after year after year, piling up on top of itself. And as those accumulations occur, enough snow and ice will start to build up. So it starts off as snow at the top, but then turns to ice at the bottom after so long and with enough pressure.
Let's say that this bowl is a mountain basin. The first year there's a light snowfall. The wind blows dusts, pollen, and other things found in the atmosphere onto the snow. The next year there's a heavy snowfall, and the volcano of a neighboring mountain erupts. The top layer of snow and ash adds pressure to the layer below. The weight of each new snowfall compresses the layers of snow below it, turning the older layers at the bottom to ice. This is how glaciers form. What do glaciers record?
The glaciers are going to record year-to-year changes. There's all these sorts of things that we can look for within the glacier to see what the atmosphere was like, how many greenhouse gases were in the atmosphere at this time. They can also look at dust to see how dry or windy a place was at that time. Pollen. Was it wet? Was it dry? We can actually even see bomb testings, volcanic ash. They can see volcanic eruptions that occurred. This kind of information can really help us look into the past and look at climate and what the atmosphere or the climate around that region was like.
Where are glaciers found?
Surprisingly enough, you can find glaciers all throughout the world. When people think of glaciers, they automatically think of the Arctic or the Antarctic, which is true, there are glaciers there. But people don't normally think that the tropics are areas that are going to have glaciers, but in fact they do. India in the Himalayas, in South America, and there are even glaciers on Africa, like Mount Kilimanjaro. You just have to go high enough up into the mountains where the snow is actually going to fall and accumulate. It's important to study several different locations rather than just one, mainly because the scientists want to get an idea of what's going on globally. So if we're going to look at the climate of the Earth in the past, we can't only go to one location. Something might have happened there that didn't happen elsewhere. We need to go to several different locations and then use the information that's found there to sort of bring it together so we can see exactly how the climate has changed on Earth as a whole. So what we've learned today is how a glacier can really give us a look into what the climate was like on Earth so many years ago. Many scientists are trying to use this information and collect it before it disappears, so they can see how Earth's climate has changed over hundreds or thousands of years.
Okay, I love that video. Super informative. There we go. Okay, hopefully when I sneezed too, it didn't interrupt your sound there. So yes, super informative video. So the difference between weather and climate is, normally I'd have you guys raise your hands and tell me, but the difference between them are weather is the state of the atmosphere in an area at any given time, where climate is the state of the atmosphere in an area over an extended period of time. So weather is current. It's the time, very second right now, today. That's weather tomorrow morning. Climate is the atmosphere of the area over an extended period of time. So if you guys want to go ahead and write those down. So weather is the state of the atmosphere in an area at any given time. Climate is the state of the atmosphere in an area over an extended period of time. So weather, the state of the atmosphere in an area at any given time. Climate, the state of the atmosphere in an area over an extended period of time. So pretty much an example of that would be today's weather is sunny, it's blue sky, but the climate of northern Utah is dry, desert, mountainous, and it has 4 seasons a year. Okay, so that leads us to the next thing in that video. What is a glacier? Normally I'd have you guys tell me what that is. So if you think you know what a glacier is from that video, go ahead and write it down. Or if you knew before, that's even awesome. That's perfect. But a glacier, from what we learned, is layer upon layer upon layer of snow, and elements of the earth and air, wind has come into that, has packed that down, and has formed, if it's cold enough, what is called a glacier. But she talked a little bit about that. But a glacier is a body of dense ice that is constantly moving. So how that had layer upon layer, it just kept growing and growing. But it slowly forms and deforms under stresses. So it could be, you know, if it's too hot that time, if it's too hot that year, it's going to melt more and it's going to ruin its foundation of that glacier. And then if it's so cold, nothing's going to happen. It's just going to keep growing its layers, right? So it's constantly moving, and it slowly forms and deforms under stresses. So that is what a glacier is. Okay, we know the differences between weather and climate, and how scientists use glaciers to learn about the past. So what they do is how she explained in that video, they go into those layers that have been building up and building up for years and years and years, and they can kind of determine from the pollens and if there was a volcano or if there was certain elements that had happened. That is how they're able to measure years and years of climate. Okay, now we know weather, we know climate, we know glaciers. The next thing we're going to dive into is air and air currents, how they affect weather. Remember, weather is the atmosphere at any given time. So let's see how air and air currents affect that. And I've got another video, so let me go ahead and screen share with you. It's called Air Currents. This one. It's very slow. Sorry, guys. Come on. There we go.
You know what I've been thinking about lately? Hanging out on a tropical beach with sand between my toes and a cool breeze blowing through my hair. I mean, strictly in the interests of science. Because the breeze in my hair and the wind and even the big cycles going on out there in the ocean are all great ways of understanding currents. A few episodes ago, we learned that the uneven heating of land and water creates wind by forming different pressure zones. The air above the land is warmer and less dense, so it rises, and the air over the water is cooler and heavier. The cool air rushes in toward the low pressure zone over the land, forming a lovely sea breeze. But you may have noticed you don't need a beach to feel a breeze. Nope. Wind is everywhere. Air is constantly moving all around the world in cycles or currents. Sometimes they're small, like a light breeze blowing off the sea, and sometimes they're massive, mighty rivers of wind. Let's see how currents move around the world. You know the Earth is a sphere, so the sun's rays hit the middle of the Earth straight on. This part of the Earth receives direct sunlight. Meanwhile, Earth's poles receive indirect sunlight, or sunlight coming in at an angle. Here, the light is spread out over a larger area and is less intense. This means the Earth's equator is much warmer than the poles. I mean, you wouldn't pack a swimsuit for a trip to the Arctic. And you know that when we have differing temperatures, we're going to have different pressure zones. The area around the equator is a low pressure zone. Here, the warm air rises and starts to slowly move towards the poles. Now, if the Earth weren't spinning on an axis, and if it didn't tilt, and if it wasn't covered in water, then the warm air at the equator would just rise toward the poles and the cool air would move in at the equator, where the warm air just left. This would create two giant air currents called cells. But, of course, things on Earth are much more interesting. The sun hits the equator, causing warm air to rise, and the air moves away from the equator, but it doesn't have time to get all the way to the poles. About a third of the way, the air cools, falls, and moves toward the equator again, creating a smaller cell. Another cell is created in the mid-latitudes and another at the poles. In each cell, cold air sinks and warm air rises. There are 6 of these cells circling in the Earth's atmosphere. And at the boundaries of these cells, something really weird starts to happen. We get jet streams. What? Air in these cells is trying extra hard to get from one pressure zone to another, since there's a big temperature difference between the air over the poles and the air over the mid-latitudes. But the Earth is spinning faster at the equator than at the poles. If you were to stand at the Earth's axis on the North Pole, you would spin around more slowly than if you were standing on the equator. So, as air rises over the equator and makes its way toward the poles, it keeps moving eastward at the same rate. Even though the higher it goes, the slower the Earth is spinning. This creates ribbons of very fast-moving air called jet streams. Jet streams move in wiggly patterns across Earth, caused by the interaction with other high and low pressure systems, and also with seasonal changes too. These streams are usually between 6 to 14 kilometers off the ground and can reach speeds of 442 kilometers per hour. Simple enough. But of course, there's more. We know from our little trip to the beach that there are other factors here. Remember our nice sea breeze? Those small differences between high and low pressure caused by the heating of the land and water taking place on on all the coastlines around the world. This makes air patterns even more complicated. And jet streams and wind patterns aren't the only currents flowing around the world. Water actually moves a lot like air. Warm, light water rises and cold, salty, heavy water sinks. And just like with air, the sun heats the water that's at the equator, and that warm water then spreads out toward the poles. Cold water slowly moving back down toward the equator where it'll warm again in an endless cycle. This massive movement of water, called ocean currents, helps regulate global temperatures just as much as air circulation. All of this interaction between the land, air, and water creates some pretty complicated wind, weather, and climate patterns. These currents make large parts of Earth livable. Without them, the poles would be far too cold and the equator scorching hot. So, currents are a little complicated and messy, and they're always on the move. They're caused by uneven heating of the Earth's surface, whether that's between land and water or between the poles and the equator, and they're all driven by energy from the sun. Without that energy, our air and water would be still. And all of these complex currents blowing and flowing around all over the place makes it really hard to predict where the wind will blow, and therefore, what kind of weather you're gonna have next week. But that's a problem we'll explore in another episode, and until then, I'm gonna keep playing.
All right, super informative, and she talks so fast. So let's recap on a few of the important things that we want to remember. Okay, so what is an air current? An air current is like a river of wind. So it's like a river, but it's of wind, and it's caused by areas of low and high pressures. And then everything we have already learned comes from its energy from the sun. So when we have these low and high pressures, that is what stirs our warm and cold air around. So what happens to the air above the water? She touched base on this a little bit, but what happens to the air above water? So the air above the water is cooler and heavier. Remember the beach scene? We had the water over here and it had the cooler, it was cooler and it was heavier. Then as it came in to land, what happens to the air above land? Does anyone remember? Think about it for a minute. What happens to the air above land? The air above land is warmer and it's dense, so it rises. So we have the cold air coming in with the water up to the land, where then the hot air is going up. So hot air rises, and that is also how we have our pressures, our low and high pressures. Okay, so air currents are caused by uneven heating of the Earth's surface of the sun. Or by the sun. So air currents are caused by uneven heating from the sun, from the surface, okay? All right, so let's do an experiment that is gonna give us a little bit more hands-on with some air pressures. Okay, so with this, you're gonna need 2 pieces of 1 foot each string. You're gonna need 2 plastic cups and some tape. Okay, and I pre-recorded this. I had Raleigh, I recruited her to help me do this experiment. So I have pre-recorded it. So I'm gonna go ahead and insert it right here. And you guys can go ahead and watch this, follow it, pause it if you need to, but do this experiment at home. So like I said, 2 1-foot pieces of string, you need 2 cups, and then some tape. And then you're also gonna need like a counter or a chair or a table, something that you can hang that string off of so those cups can hang down. You're gonna tape okay, it goes through all that in the video that I had Raleigh do. So I'm gonna go ahead and insert that right now. You guys can watch it and do the experiment with her, or you can do it when we're all done with the lesson. Okay guys, I have Raleigh here and she's gonna do this experiment, so you can follow along if you have all your supplies ready. You need 2 1-foot pieces of string, and you need tape, you need a ruler, 2 cups. So very first, I am going to have Raleigh take a piece of tape and attach one end of the string to the bottom of one of the cups, and do it for both cups. So just a small piece of tape, attach the string to the bottom of the cup. And do it for both. Okay, take the other end of the string and attach it to the edge of a table so that the cup hangs off of this side. So as far out as you can get.
Do I tape it?
Tape that string.
Like right there?
Sure. So she just left a tiny piece, if you can see that, and you're gonna do it with the second cup, but here's the trick. They have to measure 2 inches apart and they have to be the same height. So this is when you're gonna bring in your ruler, and if you need a second person to come and help you, so you need to measure them 2 inches apart. Oh, I'm not on inches. That would work better if I was on inches. Okay, so you're gonna put it right there. Perfect. You're gonna tape it and make sure, is it the same distance on the cups? Raleigh, you need to look and see if they're equal.
This one up a little.
Now it's too high, so go down
Right there?
maybe a tad more. I think that's pretty equal. I think it also depends on how you tape them on top of the cup. So they're 2 inches apart. Now, I need you to sit on the floor and you're going to blow between the 2 cups. So you're just gonna make some wind between the 2 cups.
Like that?
Yeah, sure, we're experimenting. So this is how we're gonna find out what happens and why. I wonder if there's different ways. Maybe try, blowing close.
No, it's twisting.
Okay, untwist them. And then see what happens if you just blow a consistent breath and you are closer to them. See what happens.
One's longer.
So go closer. You're blowing an individual cup. Okay, that's the experiment, and then I will explain some of this in the lesson. So back to the lesson. Okay, so kind of cool, right? Kind of interesting. It just something so simple by blowing on a cup. We don't even really think about it, right? So let's talk about how that relates to air pressure. So there was a man named Bernoulli, and he was a Swiss mathematician, and he came up with a principle. He came up with the principle saying that in areas where air moves rapidly, the pressure is low. So when you blow between the cups, you are lowering the air pressure between the cups. Blowing between the cups drops the pressure, so the higher air pressure of the surrounding areas pushes the cups together. So his theory was that he says where air moves rapidly, pressure is low. That's what he says. So us blowing or doing your experiment, blowing in between those cups is causing them to have high air pressure and pushing the cups together. So how many of you guys experienced when you blew on them that the cups would kind of crash in together? You guys saw Raleigh doing hers actually started getting tangled and stuff, but when she was consistent and close to it with her breath, it worked a little bit better. So his theory, the same principle, helps us understand that an airplane can fly due to the shape of its wings and how a pitcher can throw a curveball due to its spin. So it's all related with high and low pressures from air currents. Is that just crazy? All of this is related to weather and climate and air pressure and air currents, all of that. Okay, so our next experiment, I did not do this one. I did not pre-record it. I didn't do it. It looks super fun, so I may still try it, and if I do, I will upload this, and I will upload it and send it out to all of you guys. So I want to know if you guys do this at home. I think it would be super cool, and it's pretty easy. Most of the stuff you do have at home. So let me just go over a few things that you do need at home. And this kind of experiments, it kind of models air movement that occurs when the air is cold in one place, so like your North Pole, and hot in another, so that would be closer to the equator. So it just, the water represents, in this experiment, the water represents the lower part of our atmosphere. So in this, you will need a 9x13 glass pan. You'll need some water, a baggie of ice. You'll need some food warmer candle things or some stronger candles. You'll probably need 2 to 3 of each of 2 to 3 of those, and then some cups. And you're going to turn the cups upside down. So let me show you a picture of how this should be. If you do this, you can go ahead and pause this and look at it. So you've got your ice on one side and you've got your candles on the opposite side. So you want your cold, your North Pole on one side, and then you're closer to the equator is going to be your candles. Then you're going to put in some food coloring. Let me make sure, let me look at my notes here. I'm telling you this right. So you're going to put the blue food coloring on the ice side and the red on the other side when the water has settled. So make sure it's been sitting for a minute after you've put everything together. Then you're going to put the blue on the ice and the red on the other, and then you're going to watch the motion of the colored water. You're going to see when you put that water in, what it's going to do. Is it going to like stir all around? Is it just going to stay put in its sides? What's it going to do? So I would love it if you guys did this experiment and then shared it with me. That would be super cool. And like I said, if I end up doing it, I will upload it to, I'll put it in your parents' emails. I'll send it to them that way. But in the meantime, Bill Nye, who I know you guys love so very much, Bill Nye puts this on a much larger scale. And so I think it would be cool to have this visual of it as well. But his is much larger and he actually gets to add some air into it. So we're going to go ahead and watch that. It's a pretty short one, but it's it's taking a minute.
Guy. Bill Nye, the science guy. Bill Nye, the science guy.
Wind all over the world is caused by heating and cooling of the earth. The wind can do work. Hey, look at that. And it makes sailboats go! Wow, he went right through the door. Now, real wind doesn't come from a fan. No, in nature, wind is caused by the heat from the sun and the rotation of the earth. That's what makes these intricate patterns of clouds that we see on this photo from space. It works something like this. This is our great big plastic wind box of science. Science represents the north and south poles. Here's what happens. The sun from man warms the air over the air molecules go faster. It's further apart. So the wind much building them. Hold air and push the warm air. Those warm resistance. So it's not just they're sinking over the poles, flowing on seas, and rising over the warm earth. See, it goes around a great big circle. Inside of the earth does more than the earth is spinning. So the wind starts spinning. That's why wind comes all in directions. The wind is down.
All right, I know he's your favorite. You guys absolutely love him, don't you? Okay, here we go. I love that video though because it does show you on a bigger scale of what we're trying to kind of accomplish. So go ahead and do the experiment. If you have all the supplies, most of it is all hands-on. I mean, candles, I don't know. Hopefully you have something that you can use. It would be super cool if you could try it. I'd love to know what happens with the red water and the white or the blue water. See what happens with those currents and how it all comes together. So if you do it, let me know, send it in. And otherwise, we will see you next week. Thanks, guys.